A single misinterpreted regression coefficient inevitably leads to misallocated millions, broken supply chains, and completely failed product launches. This breakdown defines the mathematical rules of multivariate and logistic regression, establishing the technical foundation required for professional data analysis. We will deconstruct three specific pillars: coefficient interpretation, large sample asymptotics, and the mathematical fixes required for heteroscedasticity. Before calculating, we must observe the primary constraint of econometrics: correlation is distinct from causation. As this comic illustrates, assuming a trend in sales and shaved heads are linked by a causal mechanism is a logical failure. Regression models instead identify specific marginal effects, isolating the movement of one variable by forcing all other factors to remain constant. Professional success in analytics relies on identifying exactly when the underlying assumptions of a model have been violated. We begin with the theoretical ordinary least squares, or OLS, equation. The expected value of y given x equals x multiplied by beta. For continuous variables, the coefficient beta k represents the absolute marginal effect, the exact unit change in y produced by a 1-unit increase in x. This interpretation is only valid if all other independent variables in the system are held constant. Predicting umbrella sales based on weather introduces a categorical variable. Because these variables do not exist on a smooth mathematical continuum, they cannot be interpreted as continuous slopes. We code these conditions as dummy variables, 0 or 1. The baseline coefficient, B0, represents expected sales for the reference level, a sunny day. When the dummy flips to 1, the model instantly jumps vertically. This B1 coefficient represents a discrete intercept shift. Treating a categorical variable as a continuous slope creates predictions for non-existent states of weather, eroding the model's predictive accuracy. This equation predicting wages contains an interaction term, changing how we interpret the components. The hours variable is mathematically tied to education. You cannot interpret B1 as an isolated effect when multiplied by another variable in the B3 term. To find the marginal effect in an interaction, you must take the partial derivative of y with respect to x. The marginal effect of hours on wage is dynamic. Its value depends entirely on education. In this model, education is a moderator. If B3 is greater than 0, education positively moderates the effect of working hours, increasing the marginal return for every hour worked. If an interaction term is present, calculating the partial derivative is a mathematical requirement before any coefficients can be interpreted. Statistical accuracy changes as the sample size, n, grows. We must understand how estimators behave as the sample approaches infinity. In small samples, an estimator often has a wide probability distribution. We require an estimator with consistency, an asymptotic property where an estimator converges in probability to the correct population value as sample size grows. As the sample size approaches infinity, the probability distribution shrinks, collapsing onto a single vertical line representing the true population parameter, beta. This is represented mathematically. The probability limit of Bn equals beta. Clive Granger argued that if an estimator cannot converge on the truth at infinity, it has no utility in economic analysis. This transition leads to asymptotic normality. Asymptotic normality ensures that the sampling distribution of the estimator becomes normal as the sample size increases, regardless of the error term's initial distribution. A common misconception is that linear regression requires perfectly normal error terms, or epsilon, in finite samples. The central limit theorem guarantees that with a sufficiently large sample, the sampling distribution of our OLS estimator will become normal regardless of the errors. Large samples provide a mathematical safety net, allowing us to trade finite normality assumptions for unbreakable asymptotic consistency. Heteroscedasticity occurs when the variance of residuals expands as x increases. This cone-shaped data violates the assumption that variance is constant. When variance is unstable, OLS is no longer the best linear unbiased estimator because it loses asymptotic efficiency. The estimators remain consistent, but the standard errors become invalid. Consequently, all t-tests and p-values based on those errors are incorrect. Rescuing the model's robust standard errors do not change your coefficient estimates. they provide a mathematical correction that ensures hypothesis tests reflect the true variability of the data. Standard OLS faces a failure state when the outcome variable, y, is binary, meaning it only equals exactly 0 or 1. Running linear OLS on binary data results in a straight line predicting probabilities above 100% or below 0%, which is logically impossible. Logistic regression solves this by transforming the y-axis into log odds. This transformation creates a sigmoid S-curve bounded strictly between 0 and 1. This model establishes a linear relationship between the predictors and the log odds of the outcome, rather than the raw probability. We estimate this using maximum likelihood estimation, or MLE. MLE is an estimation method that finds the parameter values that maximize the probability of observing the given data. Binary data is fundamentally a log odds problem, requiring this transformation to maintain logical boundaries. Mastering this material requires identifying 3 specific mathematical conditions. First, if an interaction term is present, the marginal effect must be determined by calculating the partial derivative. Second, in large sample analysis, finite normality is traded for asymptotic consistency and estimator normality as n grows. Third, if heteroscedasticity is present, coefficients remain consistent, but White-Huber standard errors must be applied to ensure valid statistical inference. Success depends on strictly isolating variables, calculating marginal effects through calculus, and identifying assumption failures systematically. These mechanics provide the mathematical baseline for predictive accuracy and statistical integrity in professional data science.